For decades, global communication was physically anchored. You spoke into a receiver, and a copper wire carried your voice directly to another fixed point. Mobile networks introduced a major physical paradox, maintaining a reliable connection between two moving, untethered nodes across vast distances. The modern assumption is that our devices communicate through an invisible, omnipresent wireless cloud. The reality is quite the opposite. Mobile communications are overwhelmingly wired, relying on a highly structured and fortified physical infrastructure. To understand how this infrastructure operates, we must track the physics of a single call, unpack the database routing protocols that locate a moving device, and examine the mathematical multiplexing that keeps billions of signals from colliding. Analyzing this architecture requires looking past the glass screen to follow the literal physical journey of your data, step by step. The journey begins at the origin edge node, the microphone inside your phone. When you speak, you create acoustic waves. Inside the microphone, a micro-electromechanical system works with an integrated circuit to perform the first transduction. This hardware translates the fluctuating pressure of your voice into a digital baseband signal, an array of zeros and ones. An internal antenna receives this binary data and maps it onto a carrier electromagnetic wave. By altering the wave's characteristics, using high frequencies for ones and low frequencies for zeros, the phone modulates your digital voice into a radio frequency signal. These unguided radio waves are fragile. They attenuate, losing strength as they encounter physical obstacles, electrical equipment, and environmental interference. Even in a theoretical vacuum, these waves would eventually shoot off into space. The Earth's curved structure ensures they cannot follow the ground indefinitely. Because the unguided signal decays so quickly, the network has milliseconds to capture the wave before it degrades into static. This physical limit requires localized infrastructure to intercept the signal. Cellular topology solves the problem of rapid attenuation by dividing geographic areas into a grid of localized transmission zones, or cells, each anchored by its central tower. Each tower operates within a designated frequency slot. As your phone transmits the modulated radio wave outward, the closest tower in your immediate cell captures it, ensuring the signal survives. The tower functions as a critical conversion point. Inside the base transceiver boxes at the bottom of the lattice, the incoming radio wave is processed and converted into high-frequency light pulses. At this stage, your voice leaves the air. Those light pulses are injected into a subterranean network of optical fiber cables, joining a high-speed, hardwired backbone. International calls traverse oceans through armored cables laid directly on the seafloor, carrying millions of light pulses across thousands of miles. The radio transmission from your phone to the tower is the brief final mile of the connection. The vast majority of the journey occurs within solid glass. Translating a signal into light solves the distance problem, but it necessitates a routing solution. If the receiver is on another continent, the local tower must identify which specific optical fiber to use for the light pulses. The Mobile Switching Center, or MSC, serves as the central database coordinating the routing logic for a group of cell towers. When you register a SIM card, your subscription details and baseline location are stored in a primary database called your Home MSC. When you dial a number, a request hits your Home MSC, which queries the network and requests their current coordinates. The receiver's Home MSC tracks their device through several methods. It records crossing geographic cell boundaries, receives updates at set time intervals, and registers the device upon power on. If the receiver travels outside their baseline region, their Home MSC forwards the connection request to the regional database currently servicing them, the Foreign MSC. The Foreign MSC routes the request to the specific local tower where the receiver is located. This tower performs a final check to confirm the device is powered on and the line is clear. If the status is positive, the phone rings. This instantaneous connection relies on constant automated database polling and global node handshaking. Beyond routing, scaling this infrastructure introduces a physical bottleneck. Billions of users simultaneously transmit data, all competing for a severely limited band of the electromagnetic spectrum. Engineers manage this congestion through multiple access techniques, mathematical strategies used to maximize data density and prevent signal collision within finite airspace. The evolution of these techniques defines the generations of mobile technology. The 1G era relied on analog transmission using frequency division multiple access, or FDMA. This chart shows how FDMA operated. It divided the available frequency spectrum into discrete horizontal bands. Because each caller required a separate dedicated band, the total number of users a tower could handle was strictly limited. The 2G transition moved to digital signals, implementing time division and code division multiple access, TDMA and CDMA. This shift enabled SMS text messaging and basic internet browsing. TDMA and CDMA increased efficiency by slicing frequency bands into alternating micro time segments or layering them with specific mathematical codes. Multiple digital signals could then share the same frequency space without interference. The rollout of 3G widened bandwidth using wideband CDMA. Speeds reached 2 megabits per second, providing the data throughput necessary for GPS navigation and video playback, a shift that drove hardware evolution from physical keypads to the early smartphone. Each cellular generation represents a specific engineering solution to a physical problem, packing increasing amounts of digital information into finite frequency constraints. 4G required a further leap in efficiency to support high-resolution streaming media and massive simultaneous data loads in dense areas. To reach speeds of 20 to 100 megabits per second, 4G utilized orthogonal frequency division multiple access and MIMO, multiple input, multiple output. This diagram shows how multiple antennas beam discrete, spatially separated data streams to one another simultaneously. 5G expands this using massive MIMO arrays and untapped high-frequency millimeter waves, multiplying the volume of data transmitted every millisecond. The architectural purpose of 5G is to provide the low-latency connectivity required for massive networks of autonomous vehicles, smart grids, and the Internet of Things. As digital demands scale, network engineers must find new mathematical models to exploit the finite laws of physics. Tracing a call backward reveals a complex system. A connection requires rapid spectral multiplexing to leave your phone, dynamic MSC databases to calculate its route, and a massive optical backbone for physical transport. Untethered communication depends entirely on the largest hardwired infrastructure ever constructed. Finally, a local cower converts the light pulses back to radio waves. The receiver's phone catches the signal, and the MEMS speaker performs the final transduction, turning digital data back into acoustic pressure. This wireless system relies on a complex integration of optical and physical infrastructure, concealed behind a simple piece of glass. The infrastructure supporting our mobile devices remains buried underground, powered by lasers, and governed by rigid mathematical logic.